Okay, welcome. Today I am going to be giving a talk that I gave at a ICML workshop on language models and planning. And I was invited to this workshop based on some of the work that we had talked to one of the organizers about. And so this is the presentation that is there. My name is Nathan Sturdivant. I'm a professor at the University of Alberta. And this work was done with a research associate, Ehsan Fatui, and he's part of my lab, the Moving AI Lab at the University of Alberta. And we are also part of AMI, which is the Alberta Machine Intelligence Institute, and part of the CFAR AI program in Canada. And so today, what we're looking at is planning and language models. So that was the topic of the workshop. And in particular, we were looking at trying to understand what language models could and couldn't do and claims that have been made. And we'll go through these in the talk. And so this is some work that says, what can we do to really get language models to be able to do planning and to understand that process? Now, as I started this, then as we started this work, we're really thinking about some broader context. So in terms of broader context, there's a lot of claims about AI, and we want to sort of situate this work within these claims a little bit pragmatically today. But on one end, what you see is things like the Dartmouth proposal that said every aspect of learning and intelligence can be simulated by a machine. We see Haglund in his book in 1985 has a claim that we are just computers ourselves. Thinking and computing are exactly the same. And in his work thinking about AGI, Chalmers was saying that the real bottleneck is to find the right algorithms. And so there's many you can find talking about AI that will say LLMs might be that algorithm or that architecture that's going to allow us to go all the way to AGI. Pushing it back against that, there's some other voices. So Dreyfus in 2012, so this is a little bit before the modern AI revolution, but said there's no reason to think that we're making progress towards AI. And his claim is that if you're climbing a hill, it doesn't mean that you can actually get to the sky or get to the moon and beyond. So there's a question there of how far that's going to be able to take you. And we see here more recently, Pope Leo at the beginning of this year really pushed back against some of the things I had in the previous slide, saying that we really cannot equate AI with human beings. And so, we're stepping into a context. I want to just acknowledge that context in which this work is taking place, where there's arguments on either side of where this is going to lead or what the implications are. So we're a little bit more pragmatic here today. And in particular, a working definition that I have for AI is a human endeavor of using computation to achieve goals in the world. And there's a lot that could be unpacked here, but that's not for this particular lecture today or recording today. But really, the goal of this work is to say that many people had been saying that LLMs cannot plan. And we looked at some of the contexts that had been there, and we thought we could get them to plan. And so our goal was simply to say, can we take the LLM architecture and get it to do planning in ways that had failed spectacularly before? So that's what I'm going to talk about in this talk. And so let's go ahead and get started. Or get into more of the details. So there have been some, like Gary Marcus, that have said, really, we need neurosymbolic systems that are going to have a mix of both sort of the neuro component and a symbolic component. And we will talk about the value of symbolic computation a little bit later in the talk when we look at some of our experimental results. But our push here was to say, what does it take to build a system that is going to be entirely entirely neural, with no symbolic piece to it, to try to get it to plan successfully. Now, whether you want to do this in practice or how you would scale it or whatever else you're going to do with that is sort of an open question. But our question was just, can we do it? Because once we establish that it can be done, then we can establish the best ways to do it in practice. There's also been some work, and in this particular workshop, Rao Kambhampari gave the talk directly after mine. But he's been pushing and saying, look, we really don't want to think about the intermediate tokens that happen with like chain of thought reasoning, we don't really want to think them as reasoning or as thinking. And there's particularly like Drew McDermott has pushed against this notion of these words that we use like thinking. And, what do we really mean by those? So he's been saying that we shouldn't anthropomorphize these intermediate tokens. But in this particular work, we really are going to turn these intermediate traces that we're going to use into actual computational traces. And we're going to train them to do that. So we'll get to some of those details, but it's part of this broader context here, and particularly for this workshop. So we're going to do a couple of things. I'm going to tell you what they are, and then we'll look at the context of the work that's going on, some other related work, and we'll come back to exactly how we implement these things. But we're going to add a couple of ideas. One of them is called a structured context window that breaks down the context window into smaller structured pieces. We're going to use an idea called chain of computation, which is trying to riff on chain of thought, but the idea is that we're really trying to chain computation together that is going to be a much more powerful structured computation. And we're going to be training on policy traces that's going to allow an LLM or an LRM to learn a world model, to learn a policy, and learn both of these at the same time. Okay, before I get into how we're going to put these things together and make them work, let's just talk about some of the other work that's been done in establishing some of the limitations of LLMs and LRMs. And I'll just say within this talk, I'm going to sort of use LLM, LRMs, that's large reasoning models, and transformers somewhat interchangeably, just because I don't want to necessarily make a close distinction all the time between these. One paper, and again, Sammy Bengio is one of the authors on this paper, and he was giving the talk directly before me at the workshop, so he actually went into quite a bit of detail about some of the work they had done. But this gained a lot of popularity, showing that the LRMs were actually not able to do the reasoning that we might think that they were going to be able to do. In particular, they were looking at these systems that were just using the LRMs. And the stated paper of the goal is to understand the quality of the reasoning traces that are there. So there's no external symbolic system. And they found that there were huge limitations. So one of the domains, and we're going to look at a number of different domains here today, but one of the domains they looked at is Towers of Hanoi. This is running at really, really high speed here because actually Towers of Hanoi is known for having very, very long sequence of solutions. And so it's, if you're going to do a lot of computation, it's going to take many, many steps that you're going to have to replicate to get this to work properly. And so this is one of the common domains that's been used recently. And so in this particular domain, they describe this domain. We'll let the animation finish here. Here we go. And we're done. We're almost done. So we know that our solutions are exponentially long. There's lots of other interesting theoretical work that's been done recently about, so there's 3-peg, there's common recursive algorithms for that, also on 4-peg as well. And so what we're going to look at is what their input is, and we're going to look at what their output is and how they're able to achieve that. So their input here is going to be a text description, so a text input, and they're going to describe to the LRM what the problem is. So they get the world model is supposed to come from here and a complete description. And when they give this system prompt, what's happening is that they showed that as you scale the number of disks that are being solved and on the models at the time, you can see that, sure, if I have 1 disk or 2 disks, they could reliably produce the solutions. You would then start to see this drop off in behavior. And once you got to a larger number of disks, 10 to 20 disks, there's basically complete failure in being able to generate any sort of long solutions for these sorts of problems. So this was a highly publicized result that showed that the thinking that we thought was being done there, or the planning that we thought was being done, was not nearly the quality that maybe it seemed to be. Similarly, there's older work by Rao's group at Arizona State that looked at chain of thought and planning. And here they were looking at Blocksworld. So these are table to stack problems. And again, they're trying to do this entirely using an LLM and looking at what chain of thought is able to do there. So for table to stack problems, the idea is that you're going to have a bunch of blocks on the table, and I'm going to ask you to stack them up in a particular order. So that's going to look something like this, where we have an arm here. In this case, it's sorted, but they could be in a random order as they're asked to be put on the table. So in this particular work, the prompt that's being given, again, is a fully text prompt. It describes what can be done within the domain. And the hope is that given this description, these various systems would be able to solve these problems, these table to stack problems. And what you see here in results from their paper is that the fast downward planner, so a symbolic planner, is able to solve 100% of these problems up to 20 blocks with no problems. And any of these other, besides 3 blocks, any of these other, chain of thought, zero-shot type things are basically not able to solve any of these problems here. And so for some, this is a real disappointment. And it says that if you look at just the LLM or the LRM on its own, it's not able to solve these more complex problems. So there's been some other work that's tried to work around the lack of success here. One particular interesting one is an approach called searchformer. And this is a transformer that's trained on A-star search sequences. So get these traces. Well, they did a number of different ablation studies within the paper to understand what it would take to try to solve by sort of bootstrapping the transformer on these search processes. And the criteria that they use, though, for these results are that they could run it 64 times. If it was solved at least once, then they would consider it to be successful. So this is a 2024 paper. I'm not going to go into more details here, but the point is it took many, many sequences of training to get higher success rates. But I think this is an interesting approach in that it's trying to train on these sequences. And we're going to offer a different way of training on sequences that is more successful. There's also been a ton of work. So the LLM workshop I was at, there was another version of that workshop at the ICAPS conference, just right before the version that was ICML. And there was an invited talk by Hendrik Sipp. And his claim there was that actually LLMs can plan, but the way they plan is they just generate code and then you run the code to do the planning. And so there's a number of approaches that have tried this starting 2023 all the way up to even currently now. And these have been very successful. But as I said, in this particular talk, we're thinking about neural approaches. If I just use an LLM, what am I able to do with that? There are other approaches as well that have tried to sort of mix search in the generation process of an LLM or a transformer. And I'm not going to go into detail, but there's some references here, and there's other work as well. But so we were aware of this work, and then we were also aware of some theoretical work. So my colleagues at the University of Alberta, Dale Shermans and Marlos Mercado, with their student, Alex Lewandowski, had been looking and seeing that if we take a language model's output, that actually this autoregressive output is sufficient to produce these lag systems. And so they showed that theoretically, at least, there is a universal computation, like a Turing machine could be built from this. And although they've shown this theoretically, so their paper is on arXiv right now, they didn't actually build a system that could do this or could use this computational ability to do computation. But it's definitely inspired us to say, well, what would it take to take at least these ideas and turn them into something? There's also some work that's been done, right? So we have single instructions that are Turing complete. This is subtract less than or equal to, that does a subtract, a comparison, and a jump all in one. And there's some work that's been based around this. Again, they've showed that this works, but they didn't actually build computational systems based on this. And there's a sort of a hard-coded, not a trained approach. So what are we going to do? Well, a couple motivating ideas on how we get started. So the first thing we noticed is that in a large context window, there's a known problem of a needle in a haystack problem that showed that as your context window and your LLM gets really large, that it gets harder and harder to find the relevant data that you need. Now, a number of approaches have been produced for this. One of them is simply just to limit the context window when you're trying to do calculations. And that seems to actually improve the accuracy. So a large context window, in some contexts seems to be helpful, but in other contexts, not so much. And there's been other work, for instance, that's tried to say, well, when the context window gets large, let's summarize the context window and then continue with that summarized context window. And so these are ideas that are pushing on this notion that large context windows can be problematic. But again, we're going to take a different approach to that. The other thing we notice that there are these similarities between Turing machines and large language models. So if we think about it, Turing machine has a tape for doing reading and writing. An LLM has a context window that's it's reading that context window and sort of putting more symbols down. And we're thinking about like, how do we more explicitly give a language model some of the Turing machine functionality? So when we started this work, we decided to start with a model of a Turing machine that's an append-only Turing machine. And we wanted to just change slightly how the architecture of a LLM worked, so that it would have some of this functionality that looked, in this case, it's going to look like an append-only Turing machine. And we'll look at other architectures a little bit later. So the high-level approach that we're going to use is the following, is we're going to use a structured context window, which is the idea is that in the context window, we're going to break it up into fixed size blocks that can be, that are structured and that can be offered up to the LLM. We have a notion of chain of computation. So these are computational iterations where there's an ability to request the part of the context window that you want for the next portion of your computation. And then we're going to train our LM or our transformer. It's going to get policy samples. So we're going to have a general policy. We're going to train it on a bunch of examples, and it's going to need to learn the world model, and it's going to need to learn a general policy. Okay. So this is what it looks like. As I said, we have the structured context window, a chain of computation. We're going to get some sort of input prompt that comes in. We'll put that into the context window, and then we give it to the LLM to do some computation, which is going to come out and give us some intermediate states. And I'll give you the details for that in a minute. And in fact, what we're going to give it as training is we're going to give it policy examples, and we're going to say, if you get this input, these are the intermediate states that you should be generating as part of that process. So our context window has this fixed size blocks here, which we're representing by each of the lines in this table. And we're going to offer a particular set of particular operations that can be done on the context window. So remember, this is an append-only Turing machine. And so what we can do is we can choose a block on the tape, or basically in the context window, in the structured context window, that says this is where I want to use this data as my next context in my next stage of the computation. The other thing you can do is you could say I want to write a block. But if you write to a block, you have to give an address to write, and you're not allowed to overwrite because this is a append only. And so that's what it's going to have to do in terms of restrictions for these operations as part of its output. And then in each iteration, it's basically, we give the chain of computation the current structured context window. It's going to generate some output, and it has a few keywords it's allowed to generate. It's allowed to generate an append operation that says, take this particular text and put it in the structured context window at a particular location. It's going to say output. So it's going to say, here's a particular piece of text I want you to output. And that's essentially a solution that's going to go out to the user. And then it can say, here's a pointer. And this says, when you do your next structured context window computation, this is where you should be getting, where you're going to get something from the context window. And if we set the pointer to -1, then it's going to say, I'm done and I should terminate my computation. So the training is, we're assuming that we do have a policy that can be used for solving problems. And we're going to generate a whole bunch of samples, or a number. We'll have the numbers for various experiments, but we're going to show these and we're going to do batch training. And then what has to be learned is a world model, as I said before, and any mathematical operations that would be part of that world model. So we'll see in some domains, like you have to learn max and other things like that. And then it has to learn the overall policy. So let's look at this in Towers of Hanoi. Towers of Hanoi is actually relatively simple as a domain, because we don't actually have to explicitly represent the domain itself, the states in the domain. We really have to just think about the policy and generating the policy. So the input would be something like move k disks from 1 to 3 using 2 as an intermediate. And when we get into that situation, then what we wanted to do is we wanted to generate as output these three different operations. The three operations it needs to be able to generate are, if I'm moving k disks, it has to say move k to -1 from 1 to the intermediate peg, move one disk from the first to the third, and then move k -1 from 2 to 3. And so once we have that, we also could have other things like operations that say if I move one disk from 1 to 3, with intermediate is 2, then I should just output move 1 from 1 to 3. This is what the policies will give us in terms of data. In terms of the training here, so this is like what the JSON actually looks like. We have some metadata here telling us where we are in the program right now. We have the current prompt here. And this we've given in sort of more of a machine readable code here. We could make this a little bit more natural language, but at least for what we did here, we made it a little bit more like machine code. If you see this sort of request, then we're going to say put these different things at location 1, 2, and 3 on the structured context window. And then there's some other metadata here that says, and the next location, the next operation you're going to do is going to be at location 3, and the top of the stack is at location 4. Down here, if we have a prompt that just says move one item from 1 to 3, then it just says go ahead and output that, and that would be printed out. Okay. A next domain we're going to look at is the pancake puzzle. So this hasn't been used as often in the literature, but I think it's a really interesting domain, and we'll talk about that as we look at it. So in this domain, the idea is that you're a waiter, you've got a stack of pancakes, and you're trying to, with one hand, as you walk out to the table, you need to sort this set of pancakes, so you bring them to the table in sorted order. And so this is really a prefix sorting problem, because the only operation I have is this prefix flipping. I'm trying to sort the whole stack using just prefix flipping operations. Okay, so in the pancake puzzle, it's a little bit more complicated, because here I'm going to say solve a particular state to try to get to the goal, which means the policy we have is a very simple policy that's going to take exactly, well, it depends, but it will generally take two times the number of pancakes to solve the problem. And the idea is that you're going to find the largest unsorted pancake, so we'll call that K. And then you're going to flip wherever K is, that sub stack is going to get flipped to the top of the stack, giving you a new state with that flipped. We're then going to say, now we're going to flip that top one down to the location where it belongs. That will give me a new state. And then we're going to say, now go solve this new state, try to get to the goal. And looking here, I took out some of the JSON low-level details here, but we can see the state is here. It needs to find what the largest unsorted pancake is. So we're trying to put P1 on the left-hand side, sorted. And so what it's going to do is it's going to, now that it knows where that is, it's going to flip the prefix up to P1. And now P1 has to be at the bottom. So then it's going to flip P1 all the way to the bottom, and it's going to reverse that entire stack. So this is quite a bit more complicated of an operation, because we're doing that full, not only will find the largest unsorted one, but also then flipping the order in the text that comes out. And then we're going to take that new state and we'll hand it off. So we'll take that new state, we'll hand it off to the next step. Okay, we're going to look at two variants of Blocksworld that are a little bit more complicated than what was done in the previous work. The regular variant on the left is just to sort. It's going to be put everything on the table and then put them back up in a random order that's provided as part of the problem. On the right-hand side, we're going to give not just one stack, but several different stacks. So quite a bit more complicated of a problem, because you need to unstack each of the individual stacks and then put them on the table. Although the solution will be shorter, because the stacks are already a little bit unstacked for you. So for Blocksworld, it's something, we're going to actually have two parts of the policy. One is going to be an unstacking part, where you're going to say find some block that's on top of another one, put it on the table, and repeat that process. Well, basically now go solve this one and continue to unstack. Once there's nothing that's on anything else, then it's going to take all the blocks on the table and it's going to say solve these by stacking, and it's going to gradually stack them back up. Okay, so those are some of the domains we're going to look at. The size of what we're doing here is actually relatively small. So we could have started with a pre-trained transformer, but we decided to start a decoder-only transformer, no pre-training. And we're only going to train it on the different policies that we have here. Our vocabulary size is very small, only 300 words, and the number of parameters is in the tens of millions, so it's fairly tiny compared to some of the modern models. And our context window is also very, very small here. And a note about this is that when you have a very, very large context window, it's hard to predict what's going to happen. But with small context windows, we're going to get very predictable behavior that's going to work really well. And sorry, just say there is a paper available on arXiv. The link should be below this video. And if you want the full details, there's more details there about the architecture. So on Towers of Hanoi, we're actually going to train on the entire solution path with 5% holdout. So this is a fairly comprehensive training set, but we're going to do some more ablation studies with that later. On the Blocksworld, both the regular and extended and the pancake puzzle, we're going to train on 500 random configurations. We're going to have at any given size, and we're going to show what a policy is to solve those with this sequence of solution steps. And we're going to do all our testing. It's going to be one shot. So we're going to run deterministically, and it should produce the same output every single time. So what are our results? So on 3-peg Towers of Hanoi, I've just repeated the training on the left-hand side here in case anybody forgets. So with one disk, all you've got to do is move it over. We hope that we'd be able to solve that successfully, which we can. But as we scale then up, in at least the first experiment that we ran that's reported, we were able to solve 100% successfully. I mean, there's only one problem here because it's a canonical start state and a canonical goal state, but we're able to solve 100% of these problems all the way up to 15 disks, solution length 32,767. But when the solution length is 32,000, our training data is 95% of that, so that's a really high percentage. When we looked at Blocksworld, the regular Blocksworld, we're only training on 500 random configurations and showing the solution. And then we're going to test on 50 different random configurations. And we looked at this across different sizes. So we see at 6, the maximum length is 12. We're able to solve all 50 of our problems. And as we scaled up here, actually, we were able to scale all the way up to 40. As far as we ran, we're able to solve 100% of these problems. If we run with the extended problem, where we could have many different problems or many different stacks, then what would happen here is that, or what happened here in our results is that we did have 2 problems out of all the ones we tried, where there was 1 problem that we didn't solve successfully. On the pancake puzzle, though, here we are able to, again, solve all of these successfully. So this looks really, really good in that, previous approaches in trying to train and even using A-star sequences to try to train were not able to get successful solving of planning problems. And here we've been able to show that we can do that with a really high success rate. But we weren't sort of satisfied with this. And so what we wanted to do is we wanted to evaluate much more extensively. Maybe there's we only tested on 50 random problems. So maybe there's a bunch of problems we couldn't solve, but we just didn't see them. So we took n equals 8, so all Blocksworld problems, and we ran on all 8 factorial, so 40,000 initial configurations. Each of these has a different random goal state, and 100% of these problems were solved successfully. So this shows that by the training that we did, it was able to then generalize to the problems that it hadn't seen and be able to solve them as well. On the pancake puzzle, there were again 8 factorial configurations. All of these were run with a random goal state. And so random start state, random goal state. And on this, we're able to solve, I believe this is a mistake. It should say a random start state, not a random goal state. I apologize. It should be the canonical goal state and a random start state. On this, 99.99% of the problems were solved successfully with all correct actions. The only one that was failed was the goal state. And when it was given a sorted stack to begin with, it didn't terminate immediately, but it tried to just flip over the top pancake. It basically did a null operator twice, and then it terminated and said it was done. So it didn't exactly fail here. It just didn't recognize that it didn't have to do anything when it started in the goal state. Now, we wanted to look more about how much training is actually required here. And so we see in Blocksworld, as we get up to 500 training instances, and in fact, less than this, we're still able to solve 100% of the problems we were given. When we only give 5 training instances, it's not very successful, but we could handle less than 500. The extended Blocksworld actually needed all 500 training instances to be able to generalize to the multiple stacks that it was being given. On the pancake puzzle, again, it was able to, in this case, only needed 100 training instances to generalize all the way up to size 40. But when it had less than that, in this case 30, there's more results in the paper, but this is when it began to drop off. Now, in Towers of Hanoi, and I mentioned this earlier, we were seeing 95% of the data and only trying to generalize to the last 5%. And so this is actually a lot of training data that's been given here. So we went and we ran again with run this again with like a different random set and see what happens and what is the variance that we saw in these results. And we actually saw that the first time we ran it, we got lucky. We got a 100% success rate. But as we repeated this experiment, we actually saw a lower success rate overall. And so we began to analyze what was going on. Why was this failing here? And it comes down to actually the solution length. So if you remember, our append-only structured context window requires you to say what is the address where you want to write to the context window. And that means that internally, the LLM has to learn, or the transformer has to learn actually how to do addition up to the length of the plan that's being executed. And that's exponential in length. And so we, of course, could try to pre-train on numbers. So to see, like, maybe if we pre-train, it would be able to learn numbers successfully. But another approach we just tried to validate this was to say, well, what if we just have a symbolic system that's going to work externally, that when it sees an addition operator, it's going to go do the addition for us instead of requiring to be done in the neurosystem by the LLM or by the transformer. And what we see here is that if you do that, so you get rid of it, doesn't have to learn addition, that as the solution length goes up exponentially, the number of training instances that we need actually is very, very small. So the Towers of Hanoi is actually, there's a lot of repetition that goes on in these solutions. So it only takes a little bit to learn what's going on there. And then as long as I have the addition, then I can generalize up to quite large solutions. But as we began to think about this, if you think about what the Towers of Hanoi like policy looks like, you can think of the recursive policy. You sort of only need a stack to record this recursive set of operations that you're doing. And so the idea is that a append-only context window needs addition, but if we have push-pop, we don't need to have any addresses that we need to know. We just push and pop. So if the stack is really large, it doesn't matter because we don't need to know the actual address. The pointer is always going to be at the top of the stack, though, so there's some sorts of operations you won't be able to do. So what we're going to do is we're going to take our structured context window and we're going to give it essentially a push-down automata. Technically, it's a transducer because it has these output operations, but we're going to basically get push-pop and write as part of that. And so this would allow us to do things like a depth-first search, but it's not going to be Turing complete. If you have 2 stacks, then it would be, and we'll come back to that at the very, very end. So I'm not going to break this down, but what you see here is the instructions for Towers of Hanoi are much easier now because they're just push and push, basically pushes all that's going on here. And when I run the instruction, of course, I pop the instruction that I've run, and we have some output operations that go on here as well. Okay, so if we go ahead and change this append-only Turing machine and replace it with this structured context window that's based on push and pop, we're now able to, with 100% success, solve up to 20 disks. So that's up to 1 million operations, or the solution length is up to 1 million states long. And part of this is there's only 216 instructions that are needed to do this. We only trained on 80% of those, but we're still getting this great generalization. So what this shows is that we're actually able to, depending on the structure that I'm using here, we're able to still do this planning entirely in this neuro system. But it's a question of, if I have a symbolic system, then of course that could be helpful, and I would maybe be able to use different architectures. Now, before I get to the conclusions, I just wanted to put some acknowledgments in here. My lab listened to quite a few versions of this talk as we were polishing the work over the months. And I also gave a version of this talk to the Canada AI chairs and received particular feedback from Dale, Marlos, Sheila, and Jeffrey as we were thinking about this. That was really helpful. But I want to come back here and think about first what we've achieved, and then think about what are some open questions. So the first thing I would say is that without having to resort to symbolic tools, we can train language models to reliably plan using a structured context window, chain of computation, and training on general policies. If we have some numerical generalization that is given to us or we've learned it separately, that's very helpful. But we've shown that it is possible to do this and get very, very high accuracy rates. So the question is then, what are we going to do with this? Right? So this is the foundation we can build upon, because I think it's the first work that I'm aware of that really, within the LLM architecture, the transformer architecture, is able to do all of the computation there and is able to solve quite large, quite lengthy problem instances. So the question is, of course, in many of our modern LLMs, they're looking for larger and larger context windows instead of smaller context windows. So what would it mean to mix these together? I think that's a good open question. Something we're thinking about, I mean, we haven't answered this already, but I want to just point out here that right now, if you look at the way we're running things, is the state must fit inside the structured context window. And so what we're doing is we're relying on the LLM to do some of this computation of modeling the state space and what has to be done on each step. And it works as long as the state fits in the context window. But if you were to scale states up sort of arbitrarily large, then you would either have to scale up your context window, or you need to find a way to split where a state could be across multiple context windows. We have a number of ways that we're working on doing this, but this is future work, so I'm not going to talk about that too much here. But I think it's an important limitation of the current work that it requires states to fit within the context window. And then there's a question of what architecture works best. There's all sorts of architectures we could put together for doing this sort of computation. And there's also training we could very, very easily generate that would show for any sort of problem or plan we wanted to create how to turn it into a set of computations or a set of policies that look like computations on these architectures. So I think there's some interesting questions about what could be done there to try to make things work efficiently in practice. But again, this is ongoing work. So the paper is available on arXiv. And we'll be submitting this, at least at the time of the video, we'll be submitting this very shortly to conferences for review. We'd love to hear feedback from people who are interested in this, and interesting to see what now can be built on this to really get planning success. So I appreciate everybody who stayed to the end of this video. And if you didn't stay at the end, maybe you at least came to the conclusions to hear what we had to say here. And again, look forward to feedback and comments from people who are interested in this work. Thank you very much.